Hello everyone, I'm Jose Manuel Chavez and this is my argumentative exam in a video for the thermodynamics model, the thermodynamics block. And well, here is my PDF. In the screen I will present my PDF, my reading PDF of each question answer, as well as some MATLAB codes and its output, basing myself on what the certain questions are asking for. And right here I have my notebook with the exam, the same thing you're seeing right now. And well, yes, just to use it as a guide. So first off, the first question is asking us for, well, it's giving us this equation and of the Newton's law of cooling, and well, it also these questions. And the task 1.1 is asking us to get from this equation all the way to this one right here. So first off, we using some simple algebra, we take this formula and well put it right here. So now we integrate both sides, and since k is given in the given parameters is a constant, it's taken outside. And well, now using the substitution method, we get this part over here with natural logarithms of the first part of the equation plus c1, which is the constant, equals the integration of the second part of this equation. And now to cancel or to break down the natural logarithm, we we'll use the exponential to cancel out from this side, and therefore using we get over here to this part, and using some other algebra, we get to the given equation. So 1.2 is asking us to prove basically how c is a constant, and in this formula, and explain how it depends on the initial conditions. So for example, since c represents like the initial temperature difference between the object and the ambient temperature, in this specific case we're going to set the initial temperature to 0, as t as a function of time is 0 equals ambient temperature. So now substituting in the equation we just got, we cancel this out since the constant multiplies t, which is 0, and well, using some algebra, we get to c equals ambient temperature, temperature 0 divided by ambient temperature. And this means c depends on the initial conditions of the problem. And here you can see the graphical representation. So 1.3 is now giving us some certain parameters to an aluminum rod, and it's telling us to first determine the constants k and c using this data. After complete the mathematical model using this data as well, and well, after solving this with our new mathematical model, use these parameters to solve 3 in this part. So first off, in the equation we just got, we solve for c, implementing the parameters we just got, and this gives you c equals negative 260. We do the exact same for k, and after some long mathematical processes, we get to this value of here in scientific notation, or just 0.00171. And now with these given values, we substitute in the first formula, or this one over here, which gives us the mathematical model. And now obtaining the time for the given values, which is 26 Celsius, we substitute the values we just got from ck and in the same formula, and the new values for the temperatures. We get that time equals 3,251.86 seconds. So question 1.4 is now asking us to, well, this whole process we just made, to put it down on MATLAB and see the output. So here I have my MATLAB code for 1.4, which is basically the given parameters, the vectors, and after the plot. So if we run it, well, we get two curves, the heating curve and the cooling curve. So the heating curve, after the process, we can see it shows an increase as it would slowly gets to the ambient temperature, and the opposite can be said for the cooling for the cooling line, which after going after shows a decay after to neutralize to ambient temperature, not the oven temperature, which is for heating. And now 1.5, it's asking us to implement Euler's method on this MATLAB code on this problem for our heating and cooling processes. Compare the numerical solution with the analytical model by plotting on the same graph, and discuss what the analytical results represent. So here on our 1.5, where we implement Euler's method, if we run the program, we can see this, and well, this tells us that Euler's method provides an approximation of temperatures over time. The numerical and analytical solution of the comparison of these two processes is somewhat similar, identical, which confirms that Euler's method can be used. And yeah. It's just probable that we can find some minor discrepancies between the curves, and this is because of Euler's approximation, which mainly in bigger steps. So now going ahead to problem 2, this is. It's giving us the equation of quantity of heat, and it's asking us to derive an explicit expression for T for temperature over time, and explain each step in our process. So to solve this problem, we have the equation which was given, and we don't have any time, so we need to add the time to the equation with 1 over T in each side. So Q over T and 1 over T multiplied by this whole expression on the right side. We know delta T equals final temperature minus initial temperature, and the power is the quantity of heat divided by time, which is the first part of the equation. Then we have over here this, which is just using these terms are the same. After using some algebra, we get over here to this part, and now which is the equation, and using the values given on the first on the problem, we have these values, and we're just implementing on the equation. We get to this over here equation, which, if you can see, somewhat resembles y equals mx plus b, which will be used later on. So now in 2.2, it's asking us to plot the temperature versus time, generating a plot of T based on the derived expression, and ensure proper labels for accesses and descriptive title. Alright, so in this part, if we go all the way to MATLAB, in here my 2.2 is just giving parameters, the equation, and the plot. So if we run, we can see, it's a straight line, which if it resembles the y equals mx plus b equation, which is we could say it's useful for this type of problem. And now 2.3, it's asking us to use a polynomial, a 5th degree polynomial curve fitting, and use it implement it in MATLAB, and analyze and discuss what these coefficients mean. So if we go once again all the way to MATLAB, let me delete this figure. To my 2.3 here, I have the given 5th degree polynomial, and if we run this, we have this over here, which is the blue line. The blue line is the equation we already obtained, which is the linear. And over here we have the red dotted one is the new one, the 5th degree polynomial, and we can see right here this doesn't really match with the blue line all the way until here. So what does this tell us? So this basically tells us that some of the values of the polynomial function are useless, more specifically all the way until mx, which could be discussed that as well here in the as a1 over time plus a plus a sorry a 0. I can't see, sorry. And well, this means that the first values which resemble all the way from this one all the way to here are basically useless. They resemble 0 almost, which it's basically MATLAB trying to tell you it's basically MATLAB trying to tell you that these values are not necessary. They just, well, they are just there for a reason which is useless, and all the way to here, these values start getting significant to the expression, the equation, sorry. And now going all the way to problem 3, we have some given parameters of the water as well as the copper in mass, and we need to, well, use this formula over here, which is basically the quantity of heat one, but well, yeah, well, a little more complex, which it's given here. I just this part pass it all the way to the other side with this one's like inverted. This one's inverted just to obtain a positive value, and afterwards we have we know the C. Specific heat of copper in the table given is this value over here, and from water is this one. And well, all we do here is substitute values, solve for TF, and we get that the TF is 48.16. Well, yeah, that was whole problem 3. I just went a little fast. Well, now problem 4. Now this is asking us to prove, first of all, that the volumetric formula of this cone is equal to delta V equals beta times volume 0 times delta T, which we have the value, well, the formula of the volume of this cone, which is 1/3 times pi times radius squared times h. And here I have my diagram of, well, the figure, the volume of this figure O, and just the volume, just the same volume, which the volume of this figure, let's just leave it like V, and we're trying to search for VF. Here I have some equivalencies which are going to be useful when using solving for the equation. It's very important to use equivalencies as much as possible, so we can get all the way to this part where we can substitute beta for 3 alpha, and afterwards the rest of the formula of the volumetric thermal expansion is, well, we can see it's correct. And now 4.2 is asking us to calculate thermal expansion with the given values. In this equation we just have to substitute the given values, and well, first we obtain delta volume, which is this value over here. And now in this formula, which is the thermal expansion itself, we get that the final volume is 10.57875. And now, lastly, going on to problem 5, we have the gas expansion problem, which first asks us to determine if the gas increases, decreases, or remains constant in this specific figure, and afterward calculate the work done by gas. So if we go all over to my problem, we know that the ideal gas formula is over here, PV equals nRT, sorry. And well, if we using this equation that tells us that PA, VA equals NR, which are constants, by the way, are the same in both sides. But using the formula, we know B is, well, bigger in both sides, the volume, both involve volume and pressure, which means T, like temperature B, is bigger than TA, since the gas temperature increases in the process. We know it increases, like here from A to B, we can see that the line is, well, the arrow is telling us it increases. And now in 5.2 we have the values, and well, first of all, in the work done formula for ideal gas, we know this one, and we know that this integral goes well, gives us this part of the, well, this integral basically just gives this equation over here, and now all we got to do is substitute the values which are given over here, and we get that the work done is 4,800 joules. And well, that's my argumentative exam. Thank you very much for your time, and goodbye.